Now let's come back to our original discussion. As we understood what is the strategy going to be, and we have already discussed about the paper pencil binary method, and we mentioned, okay, multiplication will produce m plus n bit. If we compute n into n bit multiplication, the result will be total of them. So that's why, like, 32-bit multiplication means assuming both operand and both operands like multiplier and multiplicand are 32-bit, it will produce 64-bit of result. At each step multiplication, multiplicand needs to be placed at the right place if multiplier is bit by 1, all zeros otherwise. And final product is the sum of all steps. So that's what we did. Now, as we understood from our demonstration with an example what we are trying to do with the shifting of the register and everything, we can formulate an algorithm. So we start with a product initialized to 0, prod function, right? And then we check if the multiplier, that LSB, is 0 or not. If not, we add the multiplicand into the product, right? And then left shift the multiplicand and right shift the multiplier, and then you check if it is a 30-second repetition, then we just go out of the loop. If not, then we come back and again check the multiplier, that LSB position, whether it is 0 or not. If it is 0, then we don't need to add up anything onto the product. We just simply do the multiplicand shifting and multiplier shifting. Now, given this algorithm, what can we do on the hardware level? So we need double amount of multiplicand register. Multiplicand is 32-bit. Remember, in our example, multiplicand was 4-bit, so we placed them in an 8-bit register. Here multiplicand is 32-bit. We need to have a 64-bit register with at least a shift left capability. And then in this circuit, we are kind of started deploying with respect to deploying a multiplexer there to decide between if my last bit of multiply LSB of the multiplier is 0, then we select all 0 for addition, and if the multiplier last bit is 1, then we select the multiplicand that registers 64-bit value out of this multiplexer. So this multiplexer is 2 to 1 64-bit multiplexer. So here we are choosing between two incoming 64-bit data bus, right, information. So this is what if we want to follow up this whole algorithm, right? Here is a diamond box for decision making, right? And that decision making been replaced with a multiplexer. Remember, I said in the earlier digital component class, so multiplexer is a hardware component through which we implement decision making onto the hardware, right? So here is one example. So in the algorithm, we had to have a decision making. In that place, we placed a multiplexer to do this job. So this multiplexer output is 64-bit. Then we place an adder. Now remember, this is not a 32-bit adder. It's a 64-bit adder. And that 64-bit adder, that partial addition being to be recorded into a 64-bit register. So this doesn't need a shifting capability, just loading, parallel load, that type of register we place there. And the other operand of that adder circuit would be product itself, right? So we connect electrically this line to input back to the adder. So it becomes like an adder. Product equals product plus whatever I am placing into this through this multiplexer, right? And last but not the least, I have a 32-bit register holding the multiplier, which has to have at least a shift right capability. We can use a generic shifting register there, that's fine, but at least this register need to have a shift right capability. And this is what that our data path, we call it as a data path, like how we process through the information, right? It's like we start with that and then we need to implement the algorithm, right? Each step we shift left the multiplicand, shift right the multiplier, then we write back the product, and we carry on for 32 times, right? This whole thing. This whole controlling of the data path. So remember, this is your data path, multiplicand, then 64-bit zeros going through the multiplexer, and then multiplexer going through your adder to the product register, and product register itself is actually another operand, become another operand of the adder, and also multiplier going into some special part of the circuit. That's your data path, okay? And that special part of the circuit is the controller, okay? So let's not be very much focus on how the controller be implemented on the hardware level. Just let's try to understand the concept, what this controller does. So if we understand that, what we can do, we can write it on the Verilog, and if as with a behavioral model, like that Verilog with you that describing behavior of the controller, control here in for the multiplication, and then once you can successfully write that behavior description on the Verilog, you can actually like push it through multiple stages of tools and ultimately put it on the silicon. So that's done. That's basically is a normal process what industry follows. Now let's try to see what is the behavior of this controller. Okay, so this controller first of all controls the loading of this multiplier and multiplicand as well, and resetting these registers. So which is not shown in this figure, but this is there. This is kind of a default thing. You need to imagine that this controller issues reset signals to this multiplier, and somewhat like upon incoming request for multiplication, it takes up those multiplicand and multiplier pattern and load it onto the multiplicand and multiplier registers. Okay. So let's say they're there, and also we are not showing the clock signal. They're all register involve clock signal. So this is there just to make a clean schematic diagram. We just kind of avoiding a clock reset signal. Those are common thing. Everyone assumes that. Okay. So now upon, let's say now someone sends these two multiplicand and multiplier, these two information, and request this controller that, hey, go and multiply for me. Then what happens? This controller will go through the steps as we described previously on that flowchart for 32 times. Okay, per clock, what it will do, it will send a shift left. First of all, first to start with, it's not the shift left right away. It will, once we place the multiplicand and multiplier, right, it will go and test this multiplier LSB and send the selection signal accordingly. If the multiplier bit is 1, it will send the 1. In fact, internally you can think of it will just send this multiplier LSB directly, use that as directly as a controlling of this multiplexer. But let's assume this kind of abstract sense. It checks the multiplier LSB, this control part, and sends out corresponding selection signal to the multiplexer. And also during the same phase, it will also send a write signal into the product register. So what will happen? This part is combinational till the adder. So this multiplexer will select either 0 or the multiplicand itself, and your product was resetted to 0. So that multiplicand will be added by the adder with 0, and the result will be incoming into the product register for loading. So this write signal is basically saying product to be loading that adder and outcome of the adder. And this is one big combinational path. So you can well assume that as soon as on the first clock cycle, the selection signal is presented. It's just this addition result is just happen to be there. Let's assume instantaneously. It's not really, but let's assume for our simplicity of discussion. And then the load the addition result onto the product. And the next clock cycle, what it will do, it will send a shift left signal to the multiplicand register, shift right to the multiplier register, while keeping the right signal to low. Like, we don't want to do some accidental writing over the product. Okay, we will write the product register only when it is needed. So that is second cycle. Third clock, what it will do, it will go and again sends the select signal. Third clock, it will just make another write. Okay, fourth clock, it basically shift. Fifth clock, it is right. So it is basically alternating between shifting the registers and writing the partial product into the product register. Once this whole scenario is done, in 32 steps are done, like 32 times these whole steps are done, then controller will send a done signal to the outside wall. Whoever requested can check this. Okay, I am done. And so that you can pick up the result, 64-bit result out of the product register. So that's the hardware circuitry of binary sequential multiplier.